All right, we are on the last section of chapter 28. We are talking about the Poisson distribution, named after the guy who discovered it. So let's talk about this for a second. There's the formula for it. The probability that your random variable x takes on a specific value, little x, is m to the x times e to the negative m over x factorial. And x can take on any value, any integer value from 0 up. Okay, so there's really no limit. So Poisson is a little bit different from binomial because there was an upper limit when we were talking about binomial because there was a set number of trials. Here there's not a set number of trials. An event can happen any number of times from 0 on up. The m that they're talking about in this equation is actually the average number of times that you can expect something to happen. So that gets back to expected value. Usually you're given that piece of information or you're given some other information that you can use to calculate it. So that's what it means. All right, and the nice thing about the Poisson distribution is that the mu, your expected value, and your variance, sigma squared, are both equal to that m value. So it's kind of nice that your mean and variance are all equal to the same thing, and that happens to be the expected value of that probability distribution. So in order for something to be, or to fall under the, or to qualify as a Poisson distribution, three things have to happen. You have to have the average number of occurrences being constant for each interval. The second thing is that the probability of more than one occurrence in a given interval is very small, and then the third one is that the number of occurrences is in disjoint intervals are independent. So we'll talk about what that means. All right, so let's go through an example. We have Mr. Lee. He's planning to go fishing this weekend. Assuming that the number of fish caught per hour follows a Poisson distribution with mean 0.6, find those two things. So here's what we mean when we say the third qualifier here says that the number of occurrences in disjoint intervals are independent of each other. So when we're talking about the number of fish that he catches per hour is 0.6, that means that each hour the probability remains constant at 0.6. So the probability that he catches 2 fish, or the number of fish that he would catch in 2 hours would be 1.2 fish. And in 3 hours it would be 1.8. That would be the expected value. So as the number of hours go up, the number of fish that he catches goes up proportionally. That's all it's talking about in the third statement as to what qualifies as Poisson distribution. So first we need to figure out the probability that he catches at least 1 fish in the first hour. Now this can be done with your calculator, but let's use the formula first. We know that x is a Poisson distribution of 0.6. So let's go back to our formula. We've got m to the x, e to the negative m over x factorial. So we are looking for, he catches at least 1 fish. That means it could be 1 or 2 or 3 or 4. And since there's no upper limit, I don't really want to go on forever doing this. So what I'm going to do is I'm going to take the sum of all probabilities, which is 1, and subtract off the probabilities that I don't want. So I want 1 minus the probability that x equals 0. Okay, so for my formula, that's going to be 1 minus, now my m is this 0.6. Okay, so 0.6 to the, looking back at my formula, to the x being 0, times e to the negative m, which is 0.6, all over x factorial. So 0 factorial in this case. Okay, so just keep it clear that your m is your 0.6 and your x is the number of fish that you're talking about. We're actually subtracting off the number of fish that we don't want, but I still think of 0 as my x. Okay, and then if I calculate all of this, I get 0.451. Okay? And then, now I'm talking about the probability that he catches exactly 3 fish in 4 hours. So what happens is the 0.6 represented the number of fish per hour, but since I'm talking about the number of fish for 4 hours, my M is now going to be how many fish I would expect to catch in 4 hours. That's not 0.6 anymore, that's 4 times as big, so that's going to be 2.4. X is the number of fish that I want to catch, which is going to be 3. So I plug that into my formula. So it is going to be 2.4 to the 3 times e to the negative 2.4, and all of that goes over 3 factorial. And if you calculate that out, that's where you get 0.209. All right, so you don't actually need as much information for these questions as you did for binomial distribution. Actually makes it a little easier to calculate. The problem that you might be trying to wrap your head around is how did that formula come to be? But what I'm going to do is on the same website where your video check is, I'm going to include a PDF file that talks about the proof of why this function is the way it is. If you want to look at it, go ahead, but it is not something that's going to be required of you. So it's just there for your enjoyment, I guess. If you have any questions, you can contact me just the usual way, email, Facebook, whatever you want to do. Otherwise, I will see you tomorrow.